I've seen the announcement, slight change in the plans. I didn't record the video, but today should be pretty quickly through. It's really just taking what we know about plugging numbers into a function with one variable, x, y equals x. Actually, there's always two, but you plug in one input, you get an output. Today, we're going to plug in two inputs and get one output. So there's really three variables that we're going to be dealing with today, but I'm going to show you some techniques of how to use your graphing calculator because we have to adapt a little bit. Our tools are really not set up to do this, but I'll share a few tools with you. And then just on a personal side, I encourage you to contact your parents, your grandparents, anyone you have that's still alive, because we never know how long they're going to be with us. And my grandmother, who was 102, passed away. And, you know, when someone's 102, you think you're ready. You know, they could go at any time, right? You know, they're not going to probably get past 110, but we don't know where it is. Actually, when she was in her 90s, anyway. But what was so special about her is both her and my grandfather didn't speak English when they first went to school. She went to school about 12. She spoke Cree. She spoke a Pidgin French because they were French and Indian. But she didn't speak English. She had to learn English at school. They went to boarding schools. They were picked up in cattle trucks, shipped across state lines, and these young kids were just put in these boarding schools without parents. And things were done to them. My grandfather shared some stories. But the reason I share this with you is that's my motivation for being a teacher. I wanted to do things differently. I wanted to focus on building human development in people rather than taking society and cramming it down their throats. My grandparents, if they spoke any of the languages they knew except English, they were punished severely. And I think we can live in a world that can be multicultural, accept multiple languages, people from multiple places. And we can understand each other and we can live together. So that's kind of the legacy that my grandparents left me. My grandmother, of course, being 102, she was really the last of her generation. We don't have anyone in our family now who speaks Cree. They never taught it to their kids. So they never taught it to us. But, so that part of our culture is gone. But what lives on is the lessons. And so that's the important thing is when you've got someone that's special to you, remember to always soak in their lessons, their lives, and then use it in a way that makes our world a better place as much as possible. Of course, we probably have relatives who are a little cranky and maybe we don't want to copy what they're doing, but we can learn what not to do from some of our relatives. But anyway, we'll move forward. So today, let's go into this lesson. There we go. So really, this is just a foundation. What we're going to do next is something called partial derivatives. So we're dealing with really three variables, a function with two input variables, x and y. So we'll see how that works. It gives us a three-dimensional graph. I'll share a resource. Desmos actually has a new three-dimensional thing they're testing out. We'll give you that link so you can kind of play with it a little bit, see, so you get a visual. But today is really nothing too critical, except I'm going to share a few ways to do some of the things, because in the homework it says use a spreadsheet or something else. Well, how am I going to use it? So I spent about a couple hours on the weekend figuring out what that something else might be that you have with you, a graphing calculator. And so I'll share those techniques with you, save you those 2 hours of exploring and just get you in 5 minutes up and running. Okay. So what we're dealing with today is we're getting into what's called multivariables. And this is very important, well, for anything in the real world, but certainly for business, because in your professions, you're going to have more than one thing changing on you, more than one variable. And so this will kind of get you into that place where you can kind of track 2 or 3 variables. And as this one changes and this one changes, it's different than just having one change. But we'll also use a technique where we'll basically keep everything constant. We'll just let one change because that's what we're used to. and then we'll change these, and then we'll change these, and so we'll get ways to deal with whatever our strength is. Um, and some people, some of you, are going to be very good at multiple, kind of, you might not be good at the analyzing part of it, because that, the paper pencil, but you'll have an intuitive feel for multiple variables. And it's one of those things where women are a little bit better than men generally because of the way we're upbrought in this country or whatever, or any country, as women are a little more socialized into going into their intuition. And sometimes it goes against what we've been taught in school, but our intuition is actually going to be correct. Okay, so we can have multiple variables. Go with blue. So, here's one with three input variables, x, y, and z, a function of three variables. We're going to deal with just two. So usually we deal with f of x equals something. And really this is our y. What we're going to look at today is f of x, y with two variables. So we'll have some sort of equation that has both an x and a y in there. And what we think of as of f of x, y, that function, is really just a z variable. It's a third variable. And so instead of being able to really graph it accurately on a plane, on a piece of paper, we need 3 dimensions. So we'll go to that a little bit. Okay. So here's some examples. F of x could be just equal to x minus y. But what you're going to start seeing again is equations with more than one variable. We're going to, a little later in the week, we'll do some calculus with this called partial derivatives. That's similar to what you did in 210, and we called it implicit derivatives. So we'll see that that's basically, if you remember that part, or as we go through it, if you kind of go back to implicit derivatives, it's going to help you with the partial derivatives. So again, all we do is, if you have your x and your y, there's 2 inputs, we put them in. So we put the x in for x and the y in for y, and we get a third answer. And so, you could list this as an ordered pair, not an ordered pair, but an ordered triplet, where the 1 and 2 are the inputs and -1 is the output. So this would be a generate an x, y, and z output. Okay, that's all we're doing. We're expanding out. And if it's just kind of a little tricky, if you change the order, this is saying put y in for x and x in for y. So you can see how it, they put y in for this x, they put this x in for y, and they got this. So we'll be doing various things. The other thing is, when we use letters, there are 2 types of variables. When they use the variables at the end, x, y, z, any towards the end, those are supposed to be what we consider true variables, where we can plug in any value for them. They'll also use some letters towards the beginning of the alphabet, A, B, C, and those type of letters are supposed to signify that it's an unknown, but once you know it, it doesn't change. And we usually use those for formulas like the quadratic formula. You'll see A, B, and C. They're unknown, but so that we think of them as a variable, but they can't be anything. There is a specific value. Usually we find it and we're done. Okay, but x, y, z are those true variables where they can be usually just about anything. Okay, so we'll kind of watch that as we go through this. So again, it's just a function with 2 variables instead of 1. So instead of just plugging in x and getting an answer, we're plugging in values for x and y. And in this case, we're going to use this again. Here's a function, x squared plus y squared. And we're going to see when we graph that, we'll actually get a cone. In 2 dimensions, what we get is a circle, but we're actually going to a 3rd dimension, because remember, this function here, we'll call it g of x, y, is actually a 3rd variable, z. When we have a 3rd variable physically, that's length times width times height, so we're into 3 dimensions. Okay, and again, all we're going to do is nothing too big. We take the x and plug it in for x. We take the y and plug it in for y. do the calculations. So nothing overly new mathematically, just symbols are new. We okay so far? Okay. So here's an example, and we'll do this. You own a company that makes two models of speakers, the Ultra Mini and the Big Stack. Your total monthly cost in dollars to make X Ultra Minis and Y Big Stacks is given by this. So this is a cost function for our little speaker company. Can anyone tell me, just thinking back to single variables, 10,000 doesn't have a variable on it. What does that represent? 10,000. What's that? What kind of cost? Oh, a constant. Yeah. Okay, good. Constant. What kind of a constant? It is, thinking of economics, not math or business. It's your fixed costs, right? That's the rental of the company. This is your whatever daily whatever. It's your fixed cost because it doesn't change. Okay. Since Ultra Minis, since X is our Ultra Minis, what does this 20 in front of the Ultra Minis sort of represent? Each time we make one Ultra Mini, it costs us $20. So that's a variable cost. The more Ultra Minis, every time we make one, we're going to get 20. It's going to cost us $20 for it. Those are the parts and the labor probably. And with that in mind, how about the Big Stack? Each time we make a Big Stack, we have to spend $40. Okay, so a lot of times that's what we want you to understand is when you see any mathematical formula, you can sort of start taking the meanings out of this. They didn't tell us directly that that's what it was, but that's what we could see. That's what's going to happen in this. So that's what we did. We took a look at these one term at a time. So if we didn't make any, made 0, 0, we still have to spend $10,000, right? That's fixed cost. We signed a lease. We got to pay our rent, whether we make speakers or not. Okay, so that's what that means. Fixed cost. Good, you guys had that. Let's say in the first month that we're going to make one. Suppose you make a certain number of Ultra Minis. We don't know how many, and Big Stacks 1 month. And the next month you increase production by 1 Ultra Mini. Well, what would be our new formula? Again, even though this is a sort of a variable into a variable, we could put X plus 1 in for X. So this is like a composition. So it's just saying next month we make 1 extra. Whatever we made, they don't tell us. So we could plug that in. And so this becomes the cost function for that second month. It's not for the first month. The first month didn't have that extra speaker, but it just tells us in the second month we're going to spend an extra $20. Okay. And it's a way of saying that each, Ultra Mini speaker costs us $20 to make. We make an extra one, it's another $20. And we talked about it, the other one, the Big Stack, each time we make one of those, it's going to cost us $40. Materials and labor and all those things that go along with it. Okay. So yeah, it's just a function. Each time we make one of those, we get $20. So bringing it back to last semester, remember that's our marginal cost. You make one more, how much does it cost you? That's the marginal cost for Ultra Minis, but we also have a marginal cost for Big Stacks. So notice we have two variables, so we have two different types of marginals here. The Big Stack marginal is going to be $40. And again, we could take it right out of the equation. And this is what we call a linear function because it would actually graph as a line, but it graphs sort of in 3 dimensions because the output becomes the z-axis. So it's a little bit harder to see, but again, I'll give you a tool that will do it, but it's still a linear equation because x and y are variables to the first power. So we'll do this. And later in the semester, we get into matrices where we'll deal with like 5 or 6, but we use matrices as a technique, so we're not dealing with all these different equations. We turn them into just their coefficients. And actually, a matrix is just a collection of equations. It just is easier to work with. And we're going to show you at least the TI-84, most of the calculator, Casio, they all have ways to deal with matrices and solve them. So We plug it in, we get it. We don't have to worry, try to think about what 5 different variables are doing. Okay. And again, what we'll do is we could have this where sometimes we have so many variables all the way to n that we don't want to do x, y, z. We run out of letters, right? We could have 20 different variables. And so we put a little subscript, x1, x2, x3. And they're actually different variables. We could call them x, y, and z and multiple things. But if you have a lot, that's one technique you'll see is just x1, x2, x3. So those, just think they're different items. It might be one type of speaker. Maybe we make 10 different types of speakers. So we could have all of those. And then our formula, a linear equation, usually we have a constant. So that's our zero, A0. And A's, notice, they're unknowns, but they're not variables. They are coefficients. Once we know them, they are fixed numbers. Okay, like the 20 and the 40 from that previous example. 20 in front of the x, 40 in front of the y. Those would be our A's. Okay, so we're not going to get too much into this, so I cut a lot of these things out. But here's a quick example. X and y, the formula we might get is 3x minus 5y. And again, if this was a cost function, x costs us $3 to produce. Well, we're subtracting 5y, so maybe it's not really a cost function. But anyway, that's the idea, is every time we do y, we multiply it by 5. And but it's a linear equation because it's just x and y. Okay. Here's just another example. This is what we would call a second order function. And it's because we're taking x times y. So we could think of this as this graph, whatever it's going to be, is going to get closer to something like an x squared, a parabola, right? But it's not x squared, it's x times y, but they're 2 different variables. But remember, each of those variables can change independently. So it gives us some kind of a quadratic looking thing. But it's no longer linear. So if we were to graph this, we're going to see some curves and stuff. No longer a straight line, even being in 3 dimensions. Again, in the homework, we don't deal with any of this, but we might deal with it in the following stuff. But just thinking, now we're thinking multivariables. Sometimes it's a little scary because we got more than one thing going on, but it's just kind of like, don't worry too much. Just, it works a lot like the one variables. Okay. Another way to deal this, and we do this in statistics a lot, which we have sort of a little part in here, we do some probability, is we could also list this function as a table of values. Because a lot of times, like with speakers, you make 1, 2, 3, but you don't make 3.5 speakers, right? You can make a set value. And so no decimals, so a lot of times that leads us to having like a table. And one of the things we can use is this example they have is body, what is it? The body mass index. So how much fat you have in your body or whatever, or your, so they take your height versus your weight, and that gives you a number. And that number, if it's 25 or above, we're considered to be unhealthy, overweight. Well, we'll see what we got. So this is an example of that. So notice there are 2 variables. There's a x variable or w variable here at the top, which is your weight along the top. And then there's the height variable down along here. Fortunately, I'm off the scale. I'm a little bit more than 210, but my body index would be over 25, which I know I've been working on it for 20 years, but this is kind of where I'm at. So we'll just accept it, move forward. No, we'll keep trying to watch our diet and our weight and our exercise, but we don't know. So when we have a table, because they'll give you, I think there's one in the homework, all we have to do is the function. There's no formula, although we're going to see that we could come up with one. So to figure out what this function value is, we go to 140, which is up here. We go to 62 on the side, which is the height variable, 62 inches, and we see that this person has a body mass index, I don't know if I'm getting that, yeah, the mass index of 25.4. So they're just a little over. Maybe they should lose a little weight for their height. This one over here, we go to 210 and 63. and we find that they have a 36.9. So their body, they should either lose some weight or grow. If they were a kid, maybe they could grow. I did that. I grew out of it, but then I grew back into my problem. So that's how we look these up, though. Okay, so we can use tables. And just think, when you're doing a table, it doesn't really feel like math because you're not adding, subtracting, or multiplying, but you're doing a lookup. Okay, and in this table, the calculations have basically been done for us. But this is a nice way. We've done these for hundreds of years, or probably more than that. I had a textbook from actually Civil War I bought from a library. I just like old books, and it was just a bunch of tables for doing trigonometry. Same type of deal, where basically someone sat down, did all the calculations, and wrote them in a table because they didn't have batteries back in the Civil War. At least I don't think they did. Certainly didn't have graphing calculators, so that's how they did it. Now, this also could have, that table was generated by this formula. You take 0.45 times the weight and 0.0254 times the height. Those are, I took them out, but those are conversion factors because the formula is actually more simple than that if you're using metric. It's just weight. So this is if you have your kilograms and heights in centimeters, it's a real simple formula. So that's all those values in there come from a formula. So far, so good? Nothing too extraordinary. So this is the one I'm going to show you how to do. Now, you could probably, you could plug in these different values of x and y. So this first square, x is 10, y is 10. You could plug it in, get the number, write it down, and do it multiple times. But I'll show you sort of a shortcut that we can use is we can use our graphing calculator. And what we're going to do is we're going to fix y. First one we're going to do is 10. So what we're going to enter in for our y equals is x minus 0.3. And instead of y, I'm going to put a parentheses, and I'm going to put 10 in there. I could do the multiplication, but you'll see there's a reason why I just put 10 in there. Plus 0.75 x times 10. Okay, so I'm going to switch over to my graphing calculator. I think I can put it in the window there. Let's see. Keep all that stuff. And we're going to go to the graphing calculator. Let's move it over here. And so I'm going to, let's see. Yeah, that's small enough, but you can still see it. So I'm going to put in x. Oh, before I wanted to show you, since we were doing all that stuff, and you can see my y1 is going to shade above, and I'm not wanting to do all that shading stuff. Before I would, and what I found is if you go to here and you hit the clear button, maybe twice, notice it changed it back to a line. Okay, so it's a quick way when because we're going to do this, we're going through different types of topics, and we need to use our graphing calculators in different ways. But when we go to the other one, we don't want it. We want to just clear it out quick. So that seems to be a quick way to do it. And again, in here, I'll put in x minus 0.3. You could put 0.3. Instead of y, I'm going to put in a value. We'll put in 10. And then I'm going to put plus 0.75. You could put 0.75, same thing, x, and then parentheses 10 again. Okay, so that's going to graph this for us. It'll put in different values of x, and we'll basically be able to fill all along here when x is 10, 20, 30, 40, because what we're doing is we're keeping y always at 10. Okay, but to do this, we want to set up our table. So there's something called table set that's above the window. And again, if you have a different calculator, you can do all of this. It'll just be a little different. Casio calculators work a little different. So we want our table to start at 10, or you could have it start at 0, but for us, we just need it to start at 10, and we need the table to change by 10s because that's what's set up. Okay, and we want our independent on auto and auto. That means it will just fill in 10, 20, 30, 40. Okay, so we go second table set. And then now we're ready to go to the table, which is a blue thing above the graph. So to do that, we hit second graph, which gives us the table. And now notice it's telling us when x is 10, y is 82. Hopefully I got all these correct. I think I do. I have the answers in here. So we've got 82, 167, 152, and 337. So those are the x values going across. Oops. Let's see if I can write in here. So let's see, 80. Go backwards. I got to get my pen again. So 82, I think it was 167. Does anyone have what 30 is, or anyone put that in? 252. And then 40 was 337. And then when you go to do y is 20, what we do is we come back to the calculator. And there's two of these types of problems. So what we're going to do is we're going to go back to the y equals, and we change the 10 to 20. This is called taking a slice. We're basically, it's a three-dimensional graph, really. We're slicing through when y equals 20, so we're just going to see this. So we just come over here. That's why I put the 10 in and didn't actually do the calculation, because I just want to come in here. I'm changing all the y's to 20. So this is a technique we would use. If we had three variables, we would fix the y and the z and then just use the x changing. So we can make these tables relatively easy. It'd be nice if the calculator put a feature in here where we could change the x and y, but it doesn't seem to have it. You could do this with a spreadsheet, an Excel spreadsheet, and you could sort of change the x and y, and when you put that formula in there, it'll calculate it. But when we're on the test, what do we have? We've got a TI-84 calculator or whatever calculator we're using. And again, our table's already set up, so if we go back now, second table set, these values represent that second line. So it's 154, 313, 314, 474, so forth. I'd go back, change the y to 30, and I'll get the third row, and then change it to 40 and get the fourth row, and I can put them all in, just like that. So questions on that? Okay, but you'll see it's, you might miss a step on this, but we can go through, and I'd be happy to help you with how to use the calculator. But that'll do it for two of the problems. Now, the second problem, though, they put in just some x and y values. What you're going to want to do for that one, so let's say these x's were various values instead of 10, 20, 30. They're jumping around. Here's a way you can do that. You can go to table set, and what you can do is you can change this, arrow down, we can change this independent, which is the x variable, we can change that to ask. So when we go to the table now, it's going to ask us what do we want to put in for the x. So go second table. Nothing's here because it's waiting for me to put in. So maybe they wanted me to figure out when x is 1.1, what is y. Now I can do this. Okay, I still have to go in there and put in the y value. So there's not a way to put in x and y. But I have to manually put in the y to the formula. Does that make sense? Okay, but I can come in here, and now if they had, if y didn't change and x was the same, I could just put in the next value. If y changes, I remember I have to go back and change it in my calculation. Okay, but that'll get you through the second one because they do sort of random points all over, and it'll get you through. Again, you could also just plug them in separately, but I'm just trying to get you some technology because maybe you'll face a problem like this when you're in your job or internship or something. And I just want you to know there's ways to automate it. Automation works well if you're doing a lot of sort of similar things. So for this one, the automation worked real well. For the second question, it keeps changing. It might be easier just to manually enter them in 3 times and you're done. So you could choose either way. I think we just have one more use that we're going to do, and then we're almost done. And it's only 8:30. So most of this is just about how to use that technology. So we okay with this one? Just kind of enter it, but do sort of what they'll talk about. That's sort of a slice. We'll talk about it later. But you fix the y and let the x change. So that's a very powerful technique for analyzing multivariables. So this next part, we're going to talk a little bit about what a 3D graph is so that you can start visualizing what's going on. So we're in three-dimensional space. They just call it 3 space. And we've kind of already talked about it because that function value is really a third variable. It's, again, it's like z. So we got an x, a y as inputs, and z is our output. And just remember, even though we're thinking of this, okay, let's fix these two, and then we get a third one, in the real world, all these things are changing interchangeably. And so that takes some human intuition, and you can get there, as you go through this. But that usually doesn't come from studying math. That comes from studying a process, especially like sports. You're throwing a ball. There's the wind coming. There's this. There's that. But you'll find that humans are pretty good at adapting, or some of us are, at least, to adapting to all those changes that are going on in a sporting event. For the sports we like, at least. Playing pool. We're on a cruise ship, and the cruise ship is moving. So when we shoot, we got multiple variables. Has anyone played pool on a cruise ship? I just thought of that. That might be challenging. Yeah. It's steady, unless you're going through a storm. I remember going through a storm, and so don't play pool in a storm, I guess. That's the... Okay, so here's the 3 dimensions. So usually what we've been dealing with so far in most of our math is a XY plane, which is flat, piece of paper, we can graph. We're actually going to see that we're going to use a technique that allows us, and it's, if you, any hikers in here, kind of, have you ever used a contour map? No, they're kind of, but if you want a contour map will not just tell you where to go, it'll tell you how much elevation, because it's just 2 miles. Well, if it's 2 miles up a steep hill, that's a lot more effort than 2 miles across a flat plane. So contour maps is basically what we're going to use to take the 3 dimensions, like of this room. We could think of a corner, an x-axis, y-axis, and a z-axis. Usually what we do is we take the last axis, the z, and that one points up. Notice on 2 dimensions, we let y, because it's a later vowel or later letter, we let that point up. But that's just sort of the technique we'll do, okay? So these also produce 3 different planes. So there's sort of a XY plane, the XY plane, the YZ plane, and the YZ plane and the XZ plane. So there's all these different ones. So we could kind of, again, the technique we sort of use is we freeze 2 variables, so we're in one plane, and then we let maybe Y change. We freeze Y and Z, and we let X change. So that's how we can kind of deal with it. Or we get a tool that will do 3-dimensional graphing. Desmos didn't used to do this. I remember checking before, because I taught 3 dimensions calculus for engineers. Their second class, they start doing 3 dimensions, and you really need to be able to visualize it. But I tried Desmos again, and they do. So let's kind of just see what it is, what it looks like. I'm going to come here. We'll go to Desmos. It'll open up for us. I'm going to make it let's see, bring it down here, maybe make it a little smaller. Yeah. And so what I found with this is it's sort of in beta version or something. Yeah. But you can kind of see we get 3 dimensions here. And if you click, you can actually hold and move this around. So this just might be an extra tool that's a little helpful, so you can kind of see what's going on in the 3 dimensions. To plot a point 1, 2, 3, I found you could just do P, and you could do 1, 2, 3. I don't know if this is the correct way, but it worked. It says add a slider for P, so I hit enter. It says P is 1, and there's my point. And it might be hard to see, but what they did is they went X, they came 1 in the X direction, they went 2 in the Y direction, and then they went up 3 in the Z direction. And the way we can kind of see this Oh, there's the x. So if we go this way, we can see x. So it's come 1 in the x direction, right? It's right above the 1. We look at what's happened in the y direction. It came over 2 in the y direction. The harder one to see is z, but we'll just take its word for it that that's about 3 because that's 5 at the top. Okay, so that's all we're doing is we're plotting in 3 dimensions. Again, a little bit harder to do on a piece of paper. It'd be nice if we could make a little hologram here and we could move it. We could probably do it okay, but we just don't have really good tools to visualize these things. And then we could do the other one, which was, I think, Q. And the letters aren't so important, but they had -1, 2, 3. And what you'll see is when we plot that one, if we go this way, it went to the negative. It's the green one, actually. See, it's hard to, which way is negative, which way is positive. We could see, okay, the green one went in the negative direction with x, but it still went 2 directions in the y, and it's still right up there at 3 in the z. So you can kind of move around. And again, for points, I wouldn't worry too much, but that's all that is happening, is just like we would do x and then y. Now we do x and y and z, so we're in 3 dimensions. Okay, we'll come back to that because here we go. I told you that that's a cone. Now in 2 dimensions, if we graph x squared plus y squared, we would have it equal to a constant. What we get is we get a circle. And what we're going to see is we're going to use that circle is the concentric rings that we're going to get, because what we actually get is a cone. And if you were to take sort of different values for z, which would be our radius, you actually get a circle that it would look like a circle on that. So we'll play with this a little bit. So let's go back to Desmos. And we're going to get rid of these guys. And we will just graph that as, we could do, z equals x squared. And that's all we had. It's kind of a parabola, right? But it's a 3-dimensional parabola. And then we put the, plus y squared. Oops, squared. There we go. And I can change this color to anything I want. Well, not everything, but let's see. It's gray. I don't like gray. Let's make it red. Make it whatever color you want. But the nice thing is as we do these, you now have something that's not static, but you can move it around. And so you can kind of see it's like a cone, a parabolic cone. You can see it from underneath, from inside, side to side. So that's what that's there for. So use that link. It's in if you pull it up in mine, or just go to desmos.com/3D and you'll get it. Okay, but I think it'll be helpful in understanding what we're doing. And then what we're going to, in the homework, we don't have you do anything with this, but what we're going to do is we're going to turn this into a 2-dimensional graph where we're going to put various values of z intersecting this cone. And as you saw from the top, that will give us bigger and bigger circles. We put those down on the plane here. And so we see x and y with some circles. What we have to remember is those circles are getting higher and higher. So we're climbing up a mountain or whatever. And they use various colors. So what we're able to do, and I'll show you an example in a moment, with these concentrics, is knowing what x and y are, we're actually able to locate what the z value is. Okay, and I hope I finished up. I can't remember. I took a little break and I don't remember I came back to it, but we'll see. If not, I'll make something up. So, because we're almost done here. There's 2 questions at the end that use these concentric circles. So this is a little bit more explanation. We let z equal 1, 2, 3. You can kind of see we get these circles. We put the circles down onto the plane, and we see these circles getting bigger. But we have to think those are z values, and as we go to those points, they're getting bigger. Okay, so that's what they do, is they call this level curves. And again, if you've done a lot of hiking maps, are these sort of things, what do they call them? They call them contour maps because they give you the contour. So we see as we come out here, I'm not real. This is not on the same plane. This one here is one up. This one here is 2 high. This one here is 3, and the other one's 4. So I'm actually coming up above the page. So it's a technique that we use that we go. So here's actually a homework problem now. Oh, good, I did finish. The numbers they give you may change, but I'm just going to show you how to look up, because sometimes we land on one of the contours and that's easy to tell what the answer is. Other times we land between 2 contours and we have to sort of estimate what it's going to be. Okay, so this first one, 1, 1. Let's go with red. So that means I go 1 in the x direction and 1 in the y direction. I land right on that curve right here. So what is the z value? Exactly. It's 4 because that blue curve says 4. So that's saying that's a z value of 4. Simple, right? But would you necessarily know what to do? I didn't. This is how we read it. Now, this one's going to be a little harder. We go -1 or -2, 1. So these, remember, the first one is always the x. The second one is the y. So we go to -2, and then we go to 1. Whoops, we're not landing on a curve. So now we've got to figure out, we're about halfway between 2 curves. Does that make sense? So what do you think it is? We're between 0 and -2. What would be halfway between those two? Perfect. This one is -1. And part of the reason I could do this easily is because they gave me the answers. So I could look at it. Oh, yeah, that makes sense. So if you don't have the answers, you're kind of guessing at it. But that's exactly what that answer would be, halfway between the two. If I was 2/3 between it, it would be 2/3. But it's harder. It's estimating, right? So I think they'll only give you these. And then this one, we're supposed to estimate 3, 2.5. So again, it goes 3 in the x direction. So there's 1, 2, 3. I'm here. And then 2.5, 1, 2 and a half puts me about there. It looks to be about halfway between those two. You know, again, it's just an estimate. So I'm halfway between 4 and 6. Must be 5. Okay. Halfway between 4 and 6. So in a way you could do it is mathematically, you could say, okay, 4 plus 6 divided by 2, which gives you 10 divided by 2, which gives you 5. So if you want a sort of a formula way, you're halfway between 2 numbers, add the numbers together and divide by 2, and you'll get there. Okay. Or you just sort of, well, 4 and 6, halfway is 5. Intuition or calculation, whichever works best. Some of us work better in one mode than the other. Okay, so a couple problems at the end, and that's pretty much it. So there's going to be some formulas with x and y, and you plug in x and y. And again, you could do it in the tedious, just plug it in, calculate, you're done. Or you could try to use the calculator a bit for when there's multiple, when there's many calculations to do like the table. So I think the first 3 are just kind of sort of plug them in. There's a table. There's another one that has sort of 3 random points. Those maybe you're just going to plug it in multiple times, the same one. And then there's a few word problems, but just remember, they'll give you the equation or you'll be able to come up with it. Try with those. We can, I like to leave the word problems just as open-ended, give them a try. But a lot of times those are the kind that will end up on the test, but it's applying it, a few word problems, and then a few at the end. I think there's 2 of these with the sort of, they call them level curves. Okay. One more. Let's see. Let's just randomly say, what if I wanted -4, -3? Let's see if we can do that. 1, 2, 3, 4, right? And then down to 3. 1, 2, 3. Can you tell me what that's going to be? Can you estimate it? This is 6. This is 4. So it's getting smaller. We would say 3, but we don't know. It could have gone back up. So we're beyond our data. We can't quite, but maybe 3, maybe 2. But again, it's an estimate. And this happens to us sometimes in our business. We have data, but we don't have enough data to really know what's going on, but we take a guess. We could be right, we could be wrong. Sure. Uh-huh. Let's see. It's -2, +1. Remember that -1, though, is a z value. So it's down below the plane. So that good. It's in the second quadrant, but sometimes we have to forget. That's not so important because what we're trying to do is figure out where it is on the z. So there's this.
If it's going up in the z value, it's negative. If it's going
No,
down,
no. This, since it's negative, we would think of the positive z coming out this way, the negative z going back through the screen. So this -1 means it's down. So if this were the z, it's below, it's at the bottom. Let me come back here. Probably not very well, just to be honest, but I can show you here because this is sort of the graph we have. Oh, well, it's a little different, but z being -1 means it would be down below here somewhere, right? This one has all positive z values, and so the z value, the -1, would be down here below that axis. The answer is you actually don't need to because they're not going to get you there yet. But the reason what you see is that there's a -2 here. So analytically, you can see it's between 0 and -2, and so you have to just sort of look that we're going down to -1. So it would be there. But at this point, you won't have to locate where it's at, but you would have to see that it's going to be a -1. And part of this is as we go through, then you're getting into a different way of thinking. We're not even on this graph anymore. We're below the graph, or above the graph is where we're at. And so we're starting to get ourselves, and it's a difficult thing to do. I've taught math for 24 years. I still struggle with this. When I taught three-dimensional calculus, my students were better at visualizing it than I ever was. It's not a strength of mine. I work at it, but I'm still working at it. So this will give you a little bit of a challenge, but just think, yeah, with these things, we got this piece of paper, we're either above it or below it is what we're getting, based upon where we're here. And so you could kind of, again, if you were a hiker, what that's telling you is if you kept going here, you're going to go down into a valley, right? Over here, we're going to climb a mountain. Over here, we're climbing a mountain. And over here, we're going into a divot. So those are the kind of things to do. And again, hiking is a great way because you learn by doing. If you get it wrong, I thought I was going to go down and it would be easy. Nope, I went up. It's a hard hike, and all those sorts of things. Okay. But again, we put it together because this gives us a way to sort of visualize. Now, what would it look like if we had 4 or 5 variables? I have no clue. I had a teacher who could kind of sort of visualize 5 dimensions because that was her field of study. I have a hard time with 3, so 4 and 5. But what I can do is analyze them with a matrix, and we can still make these decisions. Okay. Questions or okay? I will take a look at the next one. I think it's going to involve a little bit more, so I'll try to get that video up and running by tomorrow so you can see it in advance. So then we can spend more time on focusing on problems and techniques. All right, thank you guys.